and Dr. Gleicher. And to join this lecture series, and Dr. Gleicher is the professor at the Department of Computer Science at UW-Madison, and his primary research interest now lies in robotics and data visualization. Today, Dr. Gleicher will give us a talk about interpreting embedding with comparison. Without further ado, please join me welcome Dr. Gleicher. And Dr. Gleicher, please just feel free to share your screen and the mic is yours.
Great. Well, thank you very much for the introduction. Let me try screen sharing. All right, so hopefully everyone can see both me and the screen. Although I apologize for a moment. Zoom has decided to reorganize everything, so I want to try and bring this back so I can see the chat just in case. So again, I'm Michael Gleicher. I'm a professor at the University of Wisconsin in the Department of Computer Sciences. Yes, for some historical reasons, the name is actually plural. In my talk today, I'm going to talk about how we can try to interpret embeddings, which are a complicated thing, using comparison as a strategy. Why is my slide not advancing? That's in our technical difficulty. My slide is not advancing. All right, nope, that doesn't do me very much. That's not advancing slide, advance. Oh, there we go. All right, sorry about that. All right, so today you're getting 5 talks for the price of 1. I'm going to talk about work in looking at embeddings, and this is work that over the years we've done basically with text embeddings, including topic models and word vector embeddings. The original work was done well, I'm going to talk about those things. I'm also going to use that as a way of motivating some of the overarching work in working with comparison. Now, the works on embeddings, these were done in collaboration with a former student, a former postdoc, Eric Alexander, who's now a professor at Carleton University in Minnesota, and Florian Heimerl, who was a postdoc and is now a teaching faculty member in my department in Wisconsin. These are a set of papers over the past few years. In fact, the most recent one will be presented next week at the IEEE-VIS conference. So the embedding work that I'll talk about at the end of this talk. Now, one thing that I always like to do when I give a talk somewhere outside of the US is to give you a sense of where I am. Madison is kind of in the north middle of the country. Yes, we call this the middle of the country, but that's because we're Americans. We're kind of weird about that. So Wisconsin is, well, that's where I am. To put it in perspective, if you know where New York or California is, we're in between them. Now, in terms of what I'm interested in, I work in a bunch of different areas. I started out traditionally, I had been working in computer graphics. I've done a lot of work with robotics, and a lot of what I do now is working with robots. But the main thing that I'm going to talk about today, or the thing I'm going to talk about today, is my work with visualization. And I like to think about this as the problem of how do we help people interact with complicated data. So I don't care if you call it data visualization or visual analytics or human data interaction, whichever term you like, it's fine. I'm going to be talking today about how we can use visual methods to help people understand some complicated kinds of things. Now, the specific thing I want to talk today is about interpreting embeddings. So we should maybe start with sort of what is an embedding. Now, within this talk, though, there's going to be the part about embeddings, a story of many people are interested in embeddings. So how do we build tools to help people work with these complicated things? But there's also going to be a kind of a counter story of an overarching piece that is woven through a lot of the research that I've done over the last while of how can we use the notion of comparison to think about how to help people work with data. Now, the problem with talking in terms of comparison is it's quite abstract, so we need something to compare. And for today, we'll use embeddings as the case study to think about comparison. So let's start by saying, well, right, what are these embedding things? Hopefully most people have a sense of that because you came to a talk about them, but just to review, right? So the idea of an embedding is we're going to take some structure and put it into a different structure. Now, this is a very mathematics definition. And as we know, mathematicians very much like to have these very abstract general definitions. In computer science, we usually mean something more specific. We usually mean to take a discrete set of objects and place them into a vector space. So here, in this example over here, you can think about my set of objects. I have a set of cities. And for every city, I'm going to come up with a list of numbers, a vector of numbers that represent that city. Now, we could think about this as this is high dimensional data. Usually we're going to need a whole bunch of numbers to say something meaningful about the objects. This example is cities. Most of the examples I'm going to show later are going to be documents. So main idea of embedding, we have objects, vectors in a high dimensional space. Now, the trick with an embedding is when we put those objects in a high dimensional space, we do it in a way that tries to create relationships so that the relationships that hold about the objects are also true about those vectors. So the most common one, and probably the main focus of this talk and most things you see with embeddings, is distance. We like the idea that if things are similar or they're close together in the semantic space, cities are like each other, then their vectors should be similar or close together in distance. The distance between them should be small. So this notion of like, these are, using the example, we have two cities. If they're similar, we would hope that in the vector space, their vectors would also be similar. Now, there are other relationships that people look for in embeddings. For example, sometimes they look for linear structure. If the vector from one object to another object using that same vector might apply to something different. Or there might be some meaningful axis in the space, some other dimension that might mean something to somebody so that say, oh, it's more of this or less of this as we move along that axis. So an important thing about embeddings is what we care about are these relationships. The actual positions don't matter. Here, A and B are close together. That's what's important. It doesn't matter if they're here or if they were over here. That isn't what makes a difference. What we care about is what's close, what's far away, or these other relationships. Now, because we care about relationships and not values, as I mentioned, the position doesn't matter. Like all of these points, they're all the same distance away. These are all valid embeddings that preserve that distance relationship for these 2 points. Now, what this means is if I take a lot of points and I embed them, I can get very different shapes that have the same relationships. So notice, like in this example here, there's this group of red points that are all close together. Over here, I have a very different embedding, but those red points, they still all stay together because this is an embedding that's trying to preserve those close neighbors. And herein you can sort of see the problem because these are very different shapes, but they're encoding the same information. They're both telling me this set of points are close together, even though so many other things have changed. Now, in embeddings, you might find lots of similarities and differences. So for example, in this set, we can see, all right, these purple ones, similarities preserved between them. The green group is close to the purple group, but the red group, over here, it's far from the green group, and here they're close together. So these relationships get very complicated, and trying to understand this kind of gets at the crux of the problem. Now, to make this a little bit more concrete, I'm going to talk about a very specific kind of embedding or application of embedding. I'm going to talk about text. When we have a set of documents, what can we do with it? And there are two ways that embeddings, or at least two, but the two I'm going to talk about for ways that we're going to use embeddings for documents. Either we're going to embed the documents themselves so that each one of those points represents a document. So if two documents are similar, they should be close together in space. If two documents are very different, they should be far away in space. Now, what we're going to do is we're going to try and estimate that distance using some computational process that understands the meanings of the texts. Now, there's a different thing we could do where rather than embedding the documents, we can try embedding the words with the idea that words that mean similar things should be close together in space. This is called a word embedding. Now, here again, we're going to have to estimate what words are similar based on some computational process. I'm not going to talk too much about the process, but I do want to sort of give a little bit of history that this is not a new idea. It goes back to the 1960s when Karen Spark Jones was really the pioneer in this, sort of said, you know, we can figure out are two documents similar by whether or not they use similar words. This is the main thing behind most document similarity metrics. The methods have gotten fancy over the past 50 years, but this is the basic idea. Documents use the same words, they're similar. So you count the words and you see, do documents use the same words? Now, it gets to be a little bit trickier than that because often you don't look for individual words, you look for groups of words. You have to worry about, well, do the words actually, are there different words that might mean the same thing? So the more modern methods get a bit fancier than that. The most commonly used method nowadays is something called topic modeling, which uses statistics of the word counts to try and build a better model of how similar documents are. What topic modeling does is it takes a document, it tries to figure out different groups of words that have similar meanings and uses those to say, do the documents use these words that have similar meanings? And that way, similar documents will use similar types of words and then become close together and measure to be similar in that vector space. So topic modeling, again, it's a common thing, but this is what's going to give us the way of measuring how similar documents are. With words, there's a similar story. We can look at words and with the idea of something called distributional semantics, which says that a word, you can figure out what a word means by the words around it. So words that are around similar other words will have similar meaning. Now, this doesn't quite always work. So notice here, I have the same sentence, but only changed the middle word. The distributional semantics say these words are similar, and in a sense they are, right? They're all nouns, they're all things that can be brown. So there is some similarity to them, even though we might say cats and cars really shouldn't be that closely compared. This process of using this to measure similarities of words leads to something called a word vector embedding. Now, word vector embeddings have become a very popular method in machine learning and natural language for two distinct sort of purposes. One is we can build these embeddings as a way to understand the documents that those words came from. This lets us find similar words and synonyms in the documents and see how words are used in a particular set of documents. Now, there's another very large application of word vector embeddings where they get used as a pre-processing step for doing natural language processing tasks. And for this, a way to think about this is it gives us a rich representation so that similar words, a system can know that words are similar and analyze them appropriately. Right. So what I just ran through in the past few minutes is several weeks worth of a machine learning course. And maybe the thing to sort of sum it up is there are ways to build word embeddings, placing each word in a way that we can measure the distance between the words. There's a few, the literature has a bunch. Word2Vec and Glove are two that were very popular 2 years ago. There are dozens of these coming out, just it seems all the time. For documents, there are several ways to build those topic models that measure the differences between documents. The most common one is a method called latent Dirichlet allocation, LDA. There's another method called non-negative matrix factorization. But the main thing to know for this talk is these measure the distances between words. These tell me how similar documents are. Now we're left with this embedding, which says for all of these things, how far are things apart? What do we do with it? So once we have one of these, why should we think about, well, it's complicated data. What might we want to learn from it? So the first thing we might want to do is we might want to look at one of these models to say, is this model any good? I've built a model that measures the distance between documents. Can I actually use that for something? I've built a model about words. Is that trustworthy enough for me to use to process and do my natural language applications? So we can also use this to gain insights into the modeling process. I have two algorithms. One produces one embedding, another produces a different embedding. How do I compare these two embeddings to see which one is better? And finally, there's this question of, I've built these embeddings. What can they tell me about the underlying data? If I can see that these words are close together, according to this, when I build the embedding from a particular corpus, or if I see that these documents are close together, what does that tell me? What can I learn from that about the entire set, the entire collection? Now, interpreting these embeddings is hard for a number of reasons. This list was originally written for why are word vector embeddings hard, but it applies just as much to document embeddings. We have large numbers of them, right? We can build a word vector embedding over hundreds of thousands of words if we have every word in the dictionary. When we embed, especially words, we tend to embed them in very high dimensional spaces. It is not uncommon to build a word vector embedding where the dimensions that we're placing the words is 150 or 300 dimensions. The relationships between words can be very complicated. Because the main thing we're interested in are distances or linear structures, the positions themselves don't mean anything. If you say, oh, it's over here, that isn't what's important. What's important is those two things are next to each other. The processes by which these are built are very complicated. I didn't say anything about those algorithms. Well, I can't really say very much about them in 1 minute. And not only are the algorithms complicated, but the things that use the results, those downstream processes. If we're going to build, say, a translation system that uses word embeddings, those systems are very complicated. So we may not be able to understand if it broke because the embedding is bad, or if there's something wrong with, say, the translation system. When we do interpretation for understanding, it's often very subjective. This notion of, oh, these two documents are similar. For example, I'm going to do recommendations. I like this document. Show me a similar document. That notion of similarity is kind of subjective. So deciding if these things are good can be very complicated. So all of those challenges lead to, okay, well, what can we do as visualization researchers to build tools to help people look at them? So first, I'm going to talk about our attempts to do this for word vector embeddings. This actually came chronologically later, but I'm going to talk about it first because it gives a sense of the process that I like to think about when we try and do these kinds of things. Now, to just sort of maybe tell you the end of this, we looked at we looked at the problem of word vector embeddings. We looked at what people did with them. We tried to understand what unique challenges they had. We did an analysis where we said, okay, what do people really need? What are they trying to do? And based on the tasks, by understanding what people wanted to do, we used that to inform what tasks weren't already served by the tools that existed. And that led us to build tools that said, okay, people have this problem. We built 3 different visual designs, each one designed to help users with one of those specific tasks. So key thing here, task, understanding what people want to do, that's what leads to designs. Now, the task analysis itself, I should mention briefly. In this case, we went through the literature, and or I should say, Florian, who was a postdoc at the time and led this project, went through a lot of literature, trying to find how were people using embeddings, all of the different things that people were doing. But one of the things that he found was hidden in there were the things they were not doing. So we could look at what people were doing and extrapolate to say, I bet that they really want to be doing this other thing, but they can't because they lack their tools. So this was sort of a combination of the literature survey to what's existing, and then a sort of a thought experiment, say, what other things should we try to come up with? Now, these use cases led us to two sort of distinct categories of tasks. One category is the category where we were trying to learn about the corpora, or the language from which the corpus came in the case of words. These are things like, you want to find similar words. You want to see, does a word have multiple meaning? Those kinds of questions. These are very much interpretation. Things like identify interesting words or interesting groups of words, probe things that you're already interested in. There's a very different kind of task, which was, I am going to use this for some downstream task. My embedding is going to be a component that I'm going to use in, say, a translation system. Therefore, I want to know, is this thing going to work well? And there's sort of two things there. One is, can we look intrinsically at the embedding? Is this a good embedding? And then actually, at the end of the day, well, even if it's a bad embedding, if it works, well, we'll take it, because ultimately we want our application to succeed. So these are very different categories of tasks, and they lead to different, as we try to be more specific about the tasks, to more specific tasks. So we came up with a set of distinct linguistic tasks, and these were tasks that dealt with one corpus. So this wasn't the which one works better or how are they different. These are specifically, I have one, what questions do I ask about it? There were a set of 7 different linguistic tasks that things ultimately sort of grouped into. And they had certain characteristics, like they involve similarity between words, or groups. And we can find multiple examples of all of them. So from this list, we could then go and look through the visualization literature and say, where were there good tools built? And there were a few papers around before our work that dealt with some of these tasks. Each one of these papers, interestingly, dealt with one specific task. And we were sort of wanting to say, well, can we get better coverage? So if we look at that list, we can see that 2 of the tasks were very well covered by prior papers. The third, if you remember, on the last one I had a third. The third one was actually not, the task was a task that isn't here. It's a task of understanding this process of building the embedding. So it didn't naturally fall into this. So it sort of falls out of the outside of this. So we don't really care about the embedding. So we kind of pushed it aside a little bit. It doesn't show up here. So what we tried to do was to come up with tools that would cover the other ones on the list. We also covered the ones that were on the list, partially because it falls into something we'd already done. So we have 3 designs, one that's based on trying to help us understand the similarities, one that's trying to help us understand the co-occurrences that cause them. Because remember, the reason that 2 words are thought to be similar is because they occur around other words. right? I had that example before where cat and car appear near brown, so the word brown brings them together. So we wanted to try and understand what causes words to come together. And also, we wanted to do something that helped understand concept axes. Are there meaningful directions in the space? Unfortunately, because of time, I'm not going to get to talk about all three of these, but let me mention the concept axes first, briefly. So the idea of a concept axis is I've placed all these points, where each one is a word, in some space. You could imagine there's some direction in the space that means something. Now, I can define that direction any way I want. I just pick some axis in the space. Here, I can say, all right, I'm going to have an animal. There's some animals that are food. There are some animals that are pets. I can make an axis from the word food to the word pet. So that defines a direction in the space. So I want to define that as a direction, maybe the food pet axis of the space. Now, it isn't going to be one of the actual things that the vector embedding was built from, but it might actually be there. So we could say, I'm going to try this vector out, and let's see, do the words actually measure out on that axis? Now, given that I have the 2 points, defining that direction, you can do simple subtraction and say, let's just take the vector between those 2 points. Or you can do some more complicated machine learning classifier kinds of things where you say, I have 2 groups, give me the direction that best separates them. For the examples that I'm going to use that simpler subtraction because, well, it actually worked pretty well. Or I'll go ahead. It works surprisingly well, even though it's simple. Now, you can do this for one axis, pick some direction. You can do this for another axis, pick a different direction. If we have 2 directions, that gives us a value for every word. We project it onto those axes. We get 2 dimensions. We can put every word someplace on a graph. So for example, in this graph, I've put the pet versus food axis and the small versus big axis. Now, I can use these axes any way I want. For example, if I built 2 different embeddings, I can put pet versus food in embedding 1 and pet versus food in embedding 2 and see what happens with that. Which is actually, all right, so this is actually not pet versus food. This is, I take a modern corpus and I say, all right, let's have from the word man to the word woman. That creates an axis. I can go from the word academic to worker. That creates another axis. And let's see, if I take those 2 axes, where do words fall? And not surprisingly, we can actually see biases in the language, that words that get associated with one gender or the other commonly in the bias of our language tend to kind of like the word captain, strong, is very far on the man axis. The word midwife, very much on the woman axis. Now, there's no like learning or anything here. This is just in the embedding. I pick a direction in space, I see where the words fall. Similarly, an author is considered very academic. A janitor is considered very much a worker. So this is more confirmatory because what I had to do is create this axis and just see what's there. It wasn't that it's a latent thing in the space. Okay, so that was concept axes. Let me talk about what we did for similarities and word being similar to each other. So the important thing with similarities is they are really the main thing that goes on in these embeddings. The distances between things, the fact that 2 things are close, is important, no matter what the values themselves are. So we want to be able to ask for a given word, well, what other words are like this? Now, the main tool for this are ordered lists, right? You say, I have a word, give me a big long list of the words that are closest to it. Now, these lists are great, but there are some problems with them because, well, you can only put so many words on the screen. You don't get any sense of relatively how far different ones are. And it's also nearly impossible to make a comparison between two different words. If I have two different words, that are the words that are similar to them close by or not. So the method that we have for this is something that we call a buddy plot. This came from actually something that I will talk about later. We actually did it first for topic models, but I'll introduce it here because they apply very nicely to word vectors. The idea with a buddy plot is I'm going to pick some object, right? Just like before I said, pick a word, give me a list of the other words, which ones are closest. I'm going to do exactly the same thing here. I pick an object, I make a list of the other things that are closest to that. It's one, and I lay them out in one dimension. So these distances are the actual distances. So if this is an object, these are the objects closest to them. They're its buddies, which is why we call it a buddy plot. Now, notice that this is not necessarily dimensionality reduction. We are mapping the distance to the horizontal axis with a focus on a similar points. The other relationships, the distances between the other objects are not encoded here. So if I have this buddy plot, that tells me that purple is closer to green. It does not tell me, well, is it this the layout or is this the layout, right? All I know is purple is closer to green. I don't know how far away it is, how far purple is from light blue. Now, this gets at kind of the other possible approaches to do dimensionality reduction. So this is an example of the embedding projector by Smilkov et al. They put a lot of words in, and the problem with embeddings is that it doesn't necessarily preserve distances that well. So around cow, you get things that are relatively close to cow, but the word that is closest to cow is cattle. If you look at the list, it's way over here. So it appears as if there's all this other stuff in between, even though there isn't, because there with hundreds of thousands of words or over 100,000 words in this embedding, they have to pack it all into 2D somehow, so you get these kinds of errors. So it's a trade-off, right? This is nice because it puts everything, it tries to capture all the distances. We're going to focus on the distances one word at a time with a buddy plot. Now, to get buddy plots to scale to more interesting questions, we can sort of use a redundant encoding where we start encoding things we use color to encode distance. So here, far away, in addition to being far in this direction, is also dark blue. Now, the next trick is I will use that color encoding not in the row itself, but in the reference row. So I have word A. These are the distances of things to word A. I have word B. These are the distances to word B. I use the distances to show, right, well, A is the right distance from B. I can also see that this point here, it is close to B because of its position, but its color comes from its position in A. So this gives me a very quick sense of not only what is close to B, but are the words that are close to B in a similar order to what's similar to A. And the nice thing about this is we can very quickly get a lot of things density. I can sort of see, oh yeah, this one here, even though this is the reference word, it has distance 0, it's far from A. But if you look at these, the colors are kind of scrambled. So the distances are kind of all over the place. If we get things that are, as this gets bigger, we can sort of look at this and see patterns where things are consistent or not within this, right? So red is far, and we can see like, yeah, for most things, far words are far, but every once in a while we see a word who doesn't follow the pattern. Now, that's good for looking at many different words. We can also do this to look at different embeddings. So let's say, well, actually what happened here is we have a corpus from different decades. We build an embedding from every decade from the 1860s to the 1990s. And this is the word broadcast. Now, today, broadcast, or ever since radio, broadcast means to tell lots of people something. The original meaning of broadcast was was a farming term. It means to cast seeds in the field. If we look at this, we can see in the 1990s, well, broadcast is similar to a bunch of words. These words are probably words like television or transmit or things like that. If we look backwards, we can see that when we get to here, the words that are closest to broadcast are words that are far away in that 1990s embedding. So we can sort of see that, well, actually very quickly between 1920 and 1930, the use of this word changed a lot. Now, hidden in there was this notion of comparison, right? What was I doing in that last example? I was comparing different embeddings. I said, do these difference, is there a difference between the 1920 embedding and the 1930 embedding? Do these distances show me something? This is about word meaning changes. We could also say, are we looking for correlations or biases? I didn't show that example. Are these models similar or different? Which is better? All of these questions are questions where we think about how do we compare two different embeddings. And in fact, those use cases, that entire category of will this work in my application, it's often comparison. I have a newer algorithm. I have a turn of a parameter. Is it going to be better or worse? This brings up that question of comparison. Up until now, I've mainly been looking at how do I extract information from an embedding? Well, comparison comes up all the time. And let me give you just sort of maybe two different ways to come at it. You might say, well, comparison is this really important problem. It is a special problem. We have to compare these two things or compare this set of things. It is special, but it is a really important special case because it comes up all the time. The number of times people say, well, my real problem is I want to compare these two things or compare this set of things. So I say, all right, it's a special case. It deserves special attention. A different viewpoint would be to say that, well, if you look at any data analysis problem, it turns out you can view it as a comparison problem. That comparison is a lens under which we can use to look at a very broad set of problems. It is a generally useful tool, and if we can learn how to study comparison, then we can learn how to design visualizations in general. Now, whether you like the right half or the left half of the slide, I don't care. They lead you to the same place. I am interested in comparison. So the question I wanted to ask, how should I think about comparison? If I want to help people do comparison, I need a better conceptual framework to think about it. Now, about 11 years ago, I came up with what I thought was the grand unified theory of comparison. And in class one day, I just wrote this whole thing out, and well, just somebody had the good sense to capture it. Like, yes, there really, this really did happen. So I had this, a lot has, the details around, but the basic idea of this grand unified theory of comparison has been around for a while. And at first the thought was, this is the secret weapon that I have. I can go around and find comparison problems and build good solutions for them because I have this great way to think about it. Well, I didn't do that. It took me a while to actually figure out how to write about it, but by 2017, 2017, I had sort of enough of this that I could write it, and there was sort of a paper that was at InfoVis in 2017 where I sort of put out this sort of way to think about comparison. And a way to think about this is I want to give you 4 questions to ask. This is the secret to how to do is if you're going to do comparison, or you want to do any visualization problem within the comparison framework, ask 4 questions that you can use when you're trying to build visualizations that involve comparison. Now, by comparison, the definition, right? So basically, you're trying to look at two or more things, and that's, I think, the main thing that makes a comparison. There are two or more objects that you're trying to understand, well, the similarities and differences between. So the four questions that I have is, first, what is the comparison? So to really try to describe it, to say what is the task? Why is the comparison hard? Right? If it's easy, then it's not, it should be, there's nothing designed for. If you can understand what the challenges are, then you can think about, well, what do I do about it? Once you've identified the challenges, you can pick a strategy of how I'm going to address those challenges, and then you can pick a visual design. So with this, the idea here is that to think about comparative tasks, I recommend talking in terms of targets and actions. So basically verbs and nouns. This idea comes from Munzner's work on Munzner's visualization taxonomy. It applies really nicely to comparison. For the challenges, by looking at a lot of visualization challenges in general, I believe that almost all the challenges in comparison boil down to questions of scale. And there are three different kinds of challenges of scale. There's a number of targets. Are you comparing a lot of things? There's how big those things are. Comparing a small number of big things or a big number of small things are both hard. And finally, there's a challenge of complex relationships, that the relationship you're looking, those similarities of why things are similar become difficult. Each of these is a question of scale. And if we look at visualization, we can sort of see that there are really just three main categories of methods we have for dealing with scale. We can scan over it. You have too many things, scan over them. We can select a subset of them and only work on a few, or we can build a summary somehow. These three strategies, well, in subsequent work, I actually believe this is the way we deal with all scalability issues in visualization. It's going to be one of these three strategies. Now, once you've figured out what your strategy is, then we can pick a visual design. And visual designs for comparison tend to fall into three categories. I shouldn't say tend to, right? Almost everyone is some combination of these three basic comparative designs. Put things next to each other, put things on top of each other, or actually show the relationship rather than the objects themselves. Now, notice that a question that was not on this slide is the question of, is the problem comparison? And I'm going to argue that that is the wrong question to ask. Just about anything can be viewed as comparison. Now, not everything benefits from being viewed as comparison. So maybe a better question is to say, does my problem benefit from me thinking about it in terms of comparison? My answer is almost always yes. So to give an example, I am going to talk about a system that we built a ways back for looking at topic models. This is a system that Eric Alexander was the first author and is the primary author of the system, and it was a system for exploring topic models. So Serendip was a system for using the topic model to guide the exploration of a corpus. We were working with literature scholars who were interested in studying a collection of documents, and they wanted tools to use the topic model to guide them to the right places to look. So a key point with their work is they were interested in things at the scale of the whole corpus. What kinds of themes are in the whole collection? They were interested in individual documents. And they were even interested in which words got used to talk about certain different kinds of topics and things like that. They were interested in all of these different scales of inquiry. One of the key points was we wanted to enable serendipitous discovery, where people didn't necessarily come in knowing what they were looking for. And for this, there were a bunch of, well, it evolved around 3 interlinked views that, because I'm already running sort of a bit behind, I'm not going to say very much about. But it's this system that lets you use the topic model and explore the topic model to see how the topic model leads to specific documents, and how those specific documents, why they are where they are in the topic model. Now, you might ask, right, is this comparison? The first thing to say is, well, no, it's not comparison. I explicitly said this is looking at a topic model. When we wrote the paper, we never described it as comparison. I'm not sure if our users were thinking in terms of comparison. However, when we were building the system, were thinking that way because, well, I like to think in terms of comparison. A way to think is, this is a tool for using topic models. That the topic model itself isn't the thing that's being compared. We're using the topic model and making comparisons of parts within the topic model. The tasks that our users actually had could be viewed as comparison tasks, even though they weren't overall comparing topic models. So, is it a comparison? Right. If you wrote your survey paper of every paper that has the word comparison in it, you'd probably miss this one. But I think it's a great example of how comparative thinking can help us with design. So the first question, right, what is the comparison? Well, to put this a little bit more precisely, the real question is, what are the elements of the comparison? How can I be specific about what is the task in terms of comparison? And remember that, well, a comparison is about pointing out, there's the verb, right? 2 or more things. So you have to have things to compare, and the idea of similarities and differences. So a thing if we're going to talk about comparisons, the way to describe a comparison task is in terms of targets. What are those things that are being compared? And what are the actions? What is the relationship? And what do you want to do with that relationship? So with comparisons, there are explicit comparisons where the system knows what the targets are, but there's also this question of implicit comparisons, where very often the thing you're comparing against is something that's in the user's head, that you compare with some target, but you don't know actually which comparison the user is doing. The user's existing knowledge is a baseline. There are all these other sort of implicit comparisons that happen all over the place. So for Serendip, what we found was a collection of different targets. Sometimes it is, does this model match my expectation? So we are really making a comparison about the model. We're comparing against the user's expectation. Are documents similar? There's a comparison of documents and groups of documents. Are there words that get used in different ways? They're comparing words. With the actions themselves, the trick there is to be a little bit more specific than just say, I want to examine or I want to compare. So here, if we look at our tasks, very often we can say, here is a good comparative verb that describes the task, measuring and quantifying the relationship, identifying things that have a relationship, taking a relationship and breaking it apart and figuring out what caused it to happen. All of these let us phrase our tasks in terms of comparison, which will help lead us to design. All right, then the question of, like, now that you have a comparison, well, why is it hard? Right, all abstractly, in Serendip, we see all of those, right? You have lots of words, you have lots of documents, you have big documents because a lot of those documents had a lot of words, and we have complicated relationships that the groupings of words lead to topics. Now, these are just some kinds of challenges. There are other challenges, like trying to say why were things similar. So I'm going to skip ahead a little bit to sort of, to not talk about the details of serendip because I'm going a little bit slowly in the beginning. But just to point out that these ideas of taking our tasks, understanding the task, describing it this way, thinking about what is the scale challenge, then could lead us to a specific design that allowed us to address it. Now, the scalability challenges for each one, if we know we have a lot of something, we can decide, do we let the user go through it in order? Do we take a subset of them? Or do we try and summarize it? By choosing which one of those strategies, that of course will then lead to design for those strategies. And then finally, when we actually go to make the visual designs that involve comparison, they're the three basic visual design strategies. We put things next to each other, we put things on top of each other, or we actually build a visualization of the relationship itself. So here we're trying to compare them so we can say show the difference. In serendip, we had examples of all of those. So sort of skipping over that a bit, the ultimate thing of should you think about things in terms of comparison? Maybe, if it helps. It often helps me. So we have this great way of thinking about comparison. Let's go back and try and apply it to the problem we had at the beginning. I have multiple embeddings. How do I compare them? So this, again, is work from Florian Heimerl, who was recently a postdoc and is now a teaching faculty at the University of Wisconsin. And the full presentation of the paper will be next week at VIS. So here, this is quite literally the comparison problem. I have two embeddings where each embedding has many objects in it, and what we care about are the local structures, the distance relationships in them. The positions in the embeddings don't matter. That was that case I showed earlier. So that initial example, these are actually two identical runs of the same algorithm, that the algorithm has some randomness in it. And notice again, in both cases, these things are close together because that's what's important. The fact the exact positions don't matter. Comparing these two, saying, yeah, these two are actually quite similar, even though they look very different, and the individuals are in very different places, that's the comparison problem. So in order to try and say, well, are these structures really similar? We're going to go through a process where, right, the first thing we have to say, can we actually measure what it means for something to be similar or different? So for this, we had to come up with a set of metrics for understanding how to measure that difference. Once you're able to measure it, then you might want to sort of say, how different are they? Or where are they different? In order to get at this, we had to build summary views that allowed us to look at these metrics over the potentially large corpora. Once you have that, now you want to try and interpret what these things mean and diagnose what's going on. To do this, we build links between the different views so we can bring the different information together to try and understand what's going on. Now, once you find a pattern, you want to then say, well, show me a specific item that falls into this pattern, identify the exemplars. And for that, we want to connect to detailed views from those summaries. And then to understand the context of an example, we need to link back to the global views. So, well, I guess that's the work that was cut out for us in building the system. So the first question, I'm going to sort of give an example of a metric, right? One thing we might say is, I have an item. Is that item the same? Does that item have the same nearest neighbor in both embeddings? It's either yes or no. And for example, in this embedding, there are, I don't know, about 800 total. For most of them, yes, they are the same, right? So this gives me a metric, and now I have a measure of similarity. Notice this metric is local. I've measured something about every single item. And for every single item, it goes into one bucket or the other. Now, I can do this. I can take that same information. I can use a color encoding where the dark blues are used for higher values. The lighter and greener are for the lower values. So here we can, yet most of them share the same nearest neighbor. Now, I don't have to just do the nearest neighbor. I could say, well, let's look at the two nearest neighbors. So with two nearest neighbors, either they share 0, they share one of their nearest neighbors, or they share both. With 5, right? Do they share 0, 1, 2, 3, 4, or 5? So this is the ones that all of the points that share the 5 nearest neighbors. So notice that this is darker. It is the highest value in the column, so I use the darkest color. Now, you might say, oh, there's a bunch of things that don't share any neighbors. These are things that are very different between the two embeddings. So I could say, well, what are those? So you can, well, in the system, you click on that box, select the things that are in that box. And if you look very carefully here, you can see little red dots scattered about. Those are the 7. And if you look at those, they tend to be things that aren't close to anything else. Now, notice here what we've done is we have a metric. The metric leads us to identify a group of things that are interesting. We could look at the list of those specific things, or we could use that to try and look at them in a different view to get some understanding of what's going on. Okay, so here's the actual list. Now, we have different views that say that measure different metrics, such as if things are not going to be near neighbors, how far do they go? That's something we call a spread view. In the interest of time, I'm just going to skip over that one. But again, one of the things we can do is link that to other groups where we can click on things here. So these are things, what this means is these were things that were near neighbors, but they went far away. We could see where they end up over in the other views. Another thing we might want to say is, well, if we take this embedding and form clusters, what clusters form? If we take this embedding and form clusters, what clusters form? They're going to be different clusters. Do those clusters match at all? So this lets us compare the clusterings. Yet another view, right? We're taking all of our distances and trying to summarize them. And here say, oh, well, this one is interesting. I can select these points. Where are they? And by linking the views together, we can start to analyze and drill into sort of see specific things that go on. Right, so there are a whole bunch of different views like that that unfortunately I don't have that much time to say things about, but let me try and make this concrete with an example. In this example, I'm comparing two different embeddings. One embedding was built from modern texts, the Wikipedia corpus. The other corpus was built from something called EBO, which is a collection of documents all written before 1700. The EBO corpus, so this, this is modern versus old. So we look at overlap, and one of the things which is maybe disappointing is that most words don't share a lot of near neighbors. This actually is an inherent thing with word embeddings, that the near neighbors, the things tend not to be that super close. If we expand this out, we're looking at the top 50, right? Most words in their top 50 are sharing, far less than half, which is kind of interesting. It means that both the stability of the methods, but also maybe that would tell us something that the language has changed. We've learned different similarities. So to look into this, what we can do is we can say, let's pick the words that do overlap a lot, that have 30, more than half, or more than 3/5 of their neighbors common. Now, these are words that are doing the same thing in both embeddings. And not surprisingly, what we find is that the words are words that haven't changed their meanings in hundreds of years. Things like numbers and days and proper names. Tuesday was a word used to describe that day of the week 400 years ago. If we then look and say, well, what about the words where there are no overlaps? That in the 50 nearest neighbors in one for the same word in one corpus and in the other corpus, what if there's no overlap, what are those words? So we can look at these words, and they actually are words that that turn out to be interesting. Some of them are words like cast, which have multiple meanings, which is a case that it isn't that well handled by the embedding methods that we used. But one that stood out is the word cup, which I think of cup as pretty much having a single meaning. However, if we look at the two closely, and this is the thing where we use that broad view, the summary view helped me find the word cup. Now I can use the detailed view to say, well, what's really going on? The word cup in the Wikipedia corpus is close towards like champion, winning, win, winners, right? This is cup like the Wimbledon Cup, the trophy that you get when you win something. Because Wikipedia tends to be news, it's going to have that usage is going to dominate. Whereas in the historical usage of cup, its cup is a drink, wine, bowl, and drinking. So the more standard usage. So this kind of shows that by using that the problem for the word cup wasn't that the word changed meanings. It's just that the Wikipedia corpus picked this other meaning as the dominant one. Let's see. I'm going to go through one last example. So here we take a data set, and the question is relating this back to topic models. I have a data set of visualization papers. I want to know, do I build a topic model from the abstracts, or do I build it from the full texts? So I build them using the same methods, and the hypothesis is that abstracts are different. And sure enough, if we do this, we see your nearest papers are very different. Most papers do not have the same nearest neighbors in common. If we look at them, we can sort of start to see a lot more of the sort of structure. If we pick some things that we think are together in one, in this case, these documents here, they do all tend to be the same, whether we're doing the abstracts or the full papers. Those, because they are they're close together, they do have lots of overlap. They tend to be higher up. They're the ones up here. Here's a cluster, though. If I select these, you can see them scattered all about. Right? One of the things that we find is that the ones that tend to group together, that in the abstracts, they are concepts that come up with similar words. In the Viz paper corpus, words like GPU and rendering. In the right, there are words that are more likely to be deeper into the domain science and words about what was being done. Okay, so these methods for comparing embeddings, there are a few limitations. Well, there's more than a few, but the big ones is, first of all, I've only shown you binary comparisons for the embeddings. It's less good for parameter tuning, where very often you want to run an experiment where you try many different values of a hyperparameter to see how things change. Another thing is, I ran through 3 out of a half dozen or so of the complicated views that we have. I will not blame anyone if like, wow, that went by too fast. I can't figure it out in 30 seconds. There's a real serious usability problem of these views work once you've mastered them. And to make that even harder, that that not only do you have to understand the view, you have to know how to use that view in conjunction with other complicated views, because the real power of the system was putting those views together. There's some issues with the scalability of the implementation, how much we can actually do. And the visual designs also run into problems if you have too many things. And finally, we've not really validated this with our target users, that typically the experiments that we ran with target users is we were holding the mouse, we were walking people through using the system. And helping them explore their data. So we were kind of using the system with them there, explaining what we were doing and seeing. We haven't really gotten to that kind of what happens if you put this in people's hands. If you want to try it, that's it. If you want to try it, it is open source, and I think that Florian now has something running where people can try it easily. Okay, so I was told that this is about the time to stop, and that's sort of good. So just to wrap up here, over the point of this talk, I've talked about using embeddings for text analysis and how we can build interpretation tools that help us interpret embeddings, to compare document and word embeddings to interpret them, to build specialized tools for understanding embeddings. And I've talked about this importance of a task-centric design process, where we think about these are the things that users are trying to do. How do we use that to try and build designs that actually support them? As the methodology for how we do that, I talked about comparison as an analysis approach. That I've talked about how we can use comparison as a way to think about design, about visualization design, so we can do comparison. I've given you some examples of how comparisons work, and I briefly mentioned the 4 considerations that give you a stepwise process for how to think about comparison. And with that, I'd like to thank you for your attention, to thank my hosts for inviting me, to thank my sponsors, and to take questions. I see there are already some in the chat.
Okay, thank you very much, Professor Mikkel, for your excellent talk. Interpreting embedding with compliance is very hard work, but it's very interesting and meaningful. Thank you again for the wonderful work and your fascinating talk. So next, let's move on to some questions.
Okay, I see the questions in the chat. Let me.
Yes, so actually we have been collecting quite a lot of questions. So yeah, I just type in the chat. So I think
okay.
Should
I just go through start at the start and go through them?
And yeah, would you mind if I also read this question, because some people, they also attending our session from the live streaming, but they couldn't see the question, so I probably need to read it so the audience.
Or maybe I will paraphrase the question, and that way also I can make sure that I'm interpreting.
Oh, that's perfect. So for the first one.
Okay, so the first question is asking about recent work about view composition. So the comparative designs that I talked about were putting things next to each other, putting things on. Actually, I should probably stop sharing. Stop sharing. Okay. The idea of, there are distinct, put things next to each other, put things on top of each other, or show the differences. And this, oops, that was, hang on, I need to, when I switched, my screen reorganized and I need to find it again. Right, so in terms of designing the individual views, that's useful to think about these as distinct cases. And then the question is, well, if we think about this as composition, where users could maybe put multiple views together, does that connect? I think that it does. I've seen some of these things with composition that work very well. I've also seen lens-based approaches where if you want to take comparison, you drag one thing over it as a comparison way. So I very much like the idea of using composition as a way to build up novel and dynamic views that you didn't necessarily know how to design beforehand. It gives us a different design language for creating new views. So I think that that's quite quite an interesting direction. So thanks for that's a great question. Of course, since that came from the stream, I don't know if that satisfies the person. So hopefully they'll also say yes, that answered the question. Okay. Okay, so the next question, this is a great question, which, oh man, that's hard. All right, so the question here as I interpret the next question is very often in doing analysis, we talk about things that are different, but you can have something which is so unexpected and that you just don't know what to do about it. That it might be that because you weren't expecting it, you don't know how to tell if it's similar or different. And this comes up very often in machine learning, where you don't know to expect something, so you don't even know that you're supposed to get the information so that you can detect it. And this is a hard problem, right? It's the unknown unknowns problem. If you don't know what to look for, it's hard to know how to look for it, or even what data that you'll want for looking for it. Wow. Do I have any, and the question is, what advice would I give? Wow, it's hard. Be brave. One of the things is, if you think you are in a case where you expect to be open to the unexpected, having tools that let you identify things that don't fit neatly into the way that you were the way you were thinking about things. So the example in the question is, I'm choosing a set of features. Try to look more broadly in ways that aren't only in terms of those features. But of course, if those features are the only thing you measure, you can't do that. So I don't think I have that much very useful to say, other than yes, that's it's an incredibly hard problem where if you don't have the information that helps you distinguish things, then it's hard to distinguish them. And even if it's hard enough, if you have the information, it's hard enough to distinguish them. That's a great question. And a lot of people are doing work on how to deal with those out of distribution things. Examples, because it's just a fundamental question. A system, you never know what you're going to encounter in the real world.
Yeah, so the third one is about the concept.
The concept act. Okay, that's a great question.
Yeah, can you check,
and I went
please?
So any concept is one axis. So if you pick two concepts, you get two axes. So for example, the one that I showed was man, woman on one axis. Then completely separately, we built an axis that was worker to academic. So they're two separate axes. They aren't necessarily orthogonal, but I drew them as a scatter plot with orthogonal axes. Now, the example that I didn't show would have been to take the same two words from two different embeddings. So the slide that I did not show was using pet to food in both the modern corpus and the historical corpus. And what happens there is, in one, you see that rabbit is on the food side, and on the other, rabbit is on the pet side, which is kind of interesting. So a good question. I'm sorry that I went through that. I think I went through everything very quickly. So
yeah. So the question 4, do you think the human and yeah, human and AI collaborations or the mixed initiative approach will become the new norm to help with the scalability issues? If so, what is your vision on it?
Oh, that's another great question. These are fabulous questions. So thank you to everyone for asking such fabulous questions. So the specific thing that was asked is having mixed initiative, right? People are bad at dealing with vast amounts of things. So that's a place where the machine might be better because machines are good. Machines are good at dealing with very large amounts of things, providing what they have to do with them are simple. That is a great place for the potential for mixed initiative. And I think, going forward in terms of analysis, understanding this in terms of task and how do we do a task assignment? What are the things that people are good at? What are the things that machines are good at? As well as how do we have them work together well? All of that needs to be addressed in order to bring forth the vision of the question of, well, there are some things that machines are better at, but they can't do the whole thing, which means we need to divide it up to the stuff the machine is good at, things that people are good at, and only then can we ask those hard questions. Well, they're all hard questions, but another hard question of how can we make it so that there's good cross between them. So I think that's a great a great big topic of how do we try to build more automation into these kinds of tools.
Yes.
All right,
so,
the next one, extending
yes,
the
do
buddy
you
plots.
think, yeah, the buddy plot can be extended by encoding additional information or maybe comparison by utilizing multiple dimension manipulations?
So let me give you, let me sort of answer a different question, which is already the buddy plots, as they get bigger and have lots of information in them, get to be very overwhelming very quickly. And I don't have any experiment or good evidence that people other than a small set of us who made them like them and can get a lot out of them. So I am concerned that they are already a very complicated design. And if we make it more complicated by packing in even more information, at some point it's just going to become too overwhelming. So maybe there might be a design, but I think first addressing some of their usability concerns will be a bigger, would sort of be, for me, more of a priority. Understanding what are the elements of their design that are so successful, where do they break, what are they good for, what are they not good for, that will help lead us to bringing in more information. The other piece of that, again, if to just sort of keep repeating this, the biggest question is task. What are we trying to do? Buddy plots are very good for certain tasks. They're very good to say, are these lists coherent and in terms of their ordering? They're good for that task. They're good for some other tasks. They're good for spotting outliers. When does something get mixed in where it's in it's in one place where you won't expect it? There's a few, they're good for a few tasks like that. Those tasks don't necessarily bring in a lot of that other information. Again, so think about what is the task that we would want to solve that requires more information. And in thinking about that task, whether or not a buddy plot and whatever successor to the buddy plot adds the features of bringing in more information, only then would I try to begin to sort of speculate, would that design work? Because I have to, what would it be working for? So hopefully that helps. It was sort of a non-answer of.
Yeah. So the next is more general, like how would you choose the dimensional reduction algorithm? And do you have to give some explanation to justify your choice?
Okay, so that's a great question of when we use dimensionality reduction, there are a lot of choices that go into the use of it. And right, so in a sense, the work that I'm talking about is once you've done dimensionality reduction, how do you look at the result? But upstream, what are they teaching you if you take the class where they teach you to use that? And I think, and this is one of the things which often gets lost in dimensionality reduction is the algorithms do very different things. Each algorithm, so if dimensionality reduction is basically applying the summarization strategy for scalability. So we talked about those strategies with dimensionality reduction. We're summarizing a lot of dimensions. Any scalability thing is about throwing away information. So you can view different dimensionality reductions as throwing away different information. So for example, if we're doing something like UMAP or TISNE, which are ones that I had used in the talk, those algorithms, the thing that they keep is neighborhood structure. If things are close in the beginning, they should be close in the end. If that's important to us, then those are the right algorithms. If we care about, say, preserving distances for longer distances, we might prefer a different algorithm. So each algorithm has some different thing that it's trying to do. And I feel that the key thing in choosing the algorithm is to first choose what do I want to try and keep, or what's important to me from that high dimensional structure, and picking an algorithm that's going to preserve that and throw away everything else, because the algorithms are going to be throwing away everything else. And I think that again, that talks to that choice of, well, what's important to you, that gets at task, right? If my task is, I want to understand what things are most similar, then I care about neighborhood structure, and those algorithms that preserve neighborhood structure are most important.
Okay. Yeah, so actually in the offline, there is a question like super relevant to this, and that is more specific. So for the comparison, like you talk about in your presentations, like one of the audience was asking, is this possible? We first transform the embedded vector first, and then do the comparison. Do you think that will achieve better performance?
Well, so I'm not sure. So the idea is, like,
we do some like translation. The example like given by the audience is like, for example, do some PCA to do the dimensional nanotube reduction, and then we do the comparison.
Yes, that is one strategy. But the thing to remember is that every time we do a dimensionality reduction, we're throwing something away. In fact, you can look at in the comparison system that we showed, each one of those metrics could be thought of as a different form of dimensionality reduction. One of them is quite literally, well, actually, you could pick PCA, but we almost always have it in the scatter plots where it shows the two scatter plots. You could do PCA. We usually use UMAP just because with embeddings, we care more about preserving local structure than global structure. And PCA is about global structure. UMAP is about local structure. But that intuition of, oh, these things are complicated, let me simplify them in some way, that will make them easier to compare. So that gives us one form of comparison. A different kind of, and you can actually even think about this as a dimensionality reduction, is I can just count the number of neighbors that are shared, right? I've gone from the high dimensional space to this very simple dimensional space where everything just has, every point just has one number. It's a count. It's a very a big dimensionality reduction. And now I look at that. So, so I think the answer to the question is yes, and that you could maybe view dimensionality reduction as a way of, as a lens to use on high dimensional data. And in some sense, the embeddings are high dimensional data. So we can use the dimensionality reduction tool as one lens for looking at it. And all these other different lenses they all fit together, and the cool things happen when you take different views on the same thing.
Yeah, thanks for the answer. And then, yeah, that is a last question. And I think we almost at the time. And yeah, I know it's pretty late for you right now, but yeah, today, we have over like 2,000 audience listening your talk.
Wow.
That's pretty impressive. And then, yeah, I can tell like audience like your talk. It's super interesting and very informative. Yeah, thank you so much.
Well, I would like to thank everybody for listening. This is fun.
Yes. Okay. And then, yeah, thanks everyone for attending the session today. And just a quick reminder for the next talk on November 4th, we will invite Dr. Eduard Groller from Vietnam University of Technology to talk about visual analysis through spatial and abstract data integrations. Hope to see you all there, and have a good rest of the day, everyone.